Hi, my name is Joshil Vaddi, and this is my motion of a falling object lab. So the purpose. So the purpose of this lab is to observe the position of an object going through freefall motion. We use two computational models, one that includes drag and one that does not have drag, and that will be compared to the real-life model, which uses tracker instead of GlowScript. Like I said, the computational models will use the GlowScript coding application. The main result will indicate the similarity between the real-life model and the computational model with drag. The other computational model without drag will also be compared to the two other models. And one assumption is that we are only tracking motion in the y-axis because it is in free fall and there is no x motion, and the x motion can be disregarded. So looking at the principles. So first let's look at the systems and surroundings. The system and surroundings include the paper ball, the meter stick, the tracker application, the glow script, and the surroundings include everything around the paper ball. The principles that we include Fg, which is equal to g times m1 m2 over r squared, and that Fg is equal to 9.8 meters per second squared, and that is the acceleration, a constant acceleration that we are seeing when the ball is dropped. And as we already know, force of gravity is equal to mass times 9.8. So now let's look at the free body diagram. So whenever we have reached terminal velocity, the force of gravity will be equal to the drag force, but in all other cases, when the ball is dropping, the drag force will actually be smaller than the gravitational force, and because of that, the forces are unbalanced, so there will be some sort of acceleration in the direction of the gravitational force. So in this case, it would be downward, and that is why the gravitational force arrow is bigger than the drag force arrow. And like again, we use this formula to computate the F drag in the computational models to simulate what the actual drag force would be. So in this case, it would be Fg minus Fd equals Fg minus Fd equals mass and acceleration. So now we have the tracker analysis. So I use this video of a paper ball dropping to track the y position of the paper ball with time. And as depicted here, it displays a curved position versus time graph. And this is expected because the velocity versus time will have a linear 9.81 slope, and then the position versus time must be curved because of the acceleration that is happening to the object. And the initial conditions are 0, 0, 0 for the position and 0, 0, 0 for the velocity, and the final position of the ball is negative 1.92 meters. So now let's look at the computational model without drag conditions. So in this case, I set the ball mass equal to 0.1 kilograms, and then we have the ball position velocity set. The time is 0, delta t 0.017, that's the size of the time step. G is 9.8, and we use these two formulas, the Newton's second law velocity formula and the position update formula, in order to calculate F net, we just did the ball and then mass times gravity to simulate Fg, and then here we did, to update the ball's velocity, we use Newton's second law, and update the ball's position, we use the position update formula. So now the with drag conditions, this is basically the same thing. We use this time constraint of t is less than 2 seconds, and the frame rate is 10. We also use the same time step, the same initial conditions, the same mass, and the velocity again is the velocity update formula present in Newton's second law, and then we do the position update formula here as well. And then we scaled the arrows this way as well. So the first one is the drag force arrow scale, and the second one is the non-drag force arrow scale computational model. So we can see that we have the position, we're updating the ball's position and the axis in the drag force positions time scale. Now these are the motions of the computational models. So you can see that they're very similar in that they show this kind of similar pattern, similar trend, this like quadratic almost. They're very similar in terms of what they're displaying, and this is a position versus time free fall data all simulated into one thing. So I made some like errors that I made include rounding errors, some tracking errors, as well as video distortion, and I also made some errors with the time. That's why we can see that this is already going through that pattern while the other two lines aren't actually like there yet, because you need to include more time in order to get the full trend of this going down like that. So I got I got less of a y position than I did if it was computational. And you can see that our model, the real life model, closely mimics the drag force model, which is a red one, closer than it does the yellow, which is one without drag force. Another error that I might have made is calculating an inaccurate drag coefficient, which might have also resulted in a reduced drag coefficient, causing this line to not be as accurate as it should be. Now we do the what if and what does it mean. So what does it mean? What is terminal velocity? So the model that considers gravity and drag as terminal velocity, and the slope plateaus and reaches a constant value. If the object was initially thrown downward, the terminal velocity in this case would remain the same, although the terminal velocity would be reached quicker if the object was thrown downward than being thrown from rest. Thank you.